Alrighty, now as we jump into this idea of implicit differentiation, we need to understand what an implicitly defined function is. So this, in the first example right here, this xy is equal to 1, that is not necessarily an implicitly defined function. And here's the reason why. We can solve for y very efficiently. And then coming up with the derivative of that isn't too much trouble because we know that's really x to the negative first. And dy over dx, by applying our famous power rule, will be negative x to the negative second, or just negative 1 over x squared. That part not so bad to do. However, when it comes to something like this, x squared minus 2y cubed plus 4y plus 2, solving for y is going to be a little bit more of a challenge because not only do we have a couple of instances of y, but we've got different powers as well on top of all that. So that's going to be a pretty huge challenge. So what do we do in a situation like that? Well, what we must do is we must sort of kind of fudge our way through using what's called implicit differentiation. Okay. So implicit differentiation, this is the process of differentiating, and when you do, it's dy over dx, and it's taking place with respect to x. This means that when you differentiate terms involving an x alone, you can just go forward like you're used to. However, when you're differentiating terms involving y, you must apply the differential. And that differential specifically is dy over dx, because you are assuming that y is defined explicitly. And this allows us to handle functions, or I shouldn't necessarily say functions, but I should say equations. And those equations involve, conic sections like ellipses and hyperbolas and circles and such. Okay, so let's talk about these two right here, a and b. All I'm doing in a is just simply differentiating something that's involving x's only. So that's not hard to do. The derivative is 3x squared. But when it's only y's, what I need to do is tack on that differential, as previously said. So the derivative here will be 3y squared. You just follow your normal rules like you would for x's, but then you must tack on dy over dx. And really, that's the only difference between implicit differentiation and so-called regular differentiation. So let's take a look at this one right here that has a mix of terms. Now, fortunately, they're being added, so that shouldn't be too much trouble. The derivative of x is 1, and the derivative of 3y is just going to be 3, but I tack on dy over dx. Now, this one down here, this one is a little bit more interesting because we have to deal with something called the product rule. Oh no, oh yes. Okay, so when we deal with the product rule, we have to think of this x as my u, and we have to think of this y squared as my v. So when I go to do the product rule, it's going to be u prime, which is 1, times v, which is y squared. And then I go back and I add in my u, which is x, times my v prime, which is going to be 2y dy dx. So that's where the dy dx comes in. So kind of cleaning up a little bit here, it's going to be y squared plus 2xy dy over dx. And that would be your derivative of that one. Okay, so why don't you go ahead and try this example here. Find dy over dx. Well, when we go to do that, we're going to get 2y dy over dx is equal to 1. But we specifically said to find dy over dx. Well, lucky for us, that's easy to do because I just need to isolate that differential, and I can do that by dividing both sides by 2y. So dy over dx is equal to 1 over 2y, and there is our implicit derivative. Okay, so In order to do this efficiently, what we're going to do is differentiate both sides of the equation with respect to x. And that might mean tossing in a differential, and that just might have to happen from time to time. We'll collect the terms that have dy over dx on one side of the equation. And then the really slick trick here is to factor out dy over dx and then finally solve for that dy over dx. Let's take a look at a couple of examples and see how it's going to work. All right, so to find implicitly defined derivatives, it's really not too bad. We're just going to differentiate both sides of an equation here to start, and the goal is to get the dy over dx by itself. So if I differentiate the left side here, I'm going to have 2y dy over dx. And differentiating the right side, I'm going to get 2 plus 3 dy over dx. Okay, now it's a matter of getting the dy over dx's on the same side and doing a little bit of factoring and division. So let's pull this over to the left side. We get 2y dy over dx minus 3 dy over dx is equal to 2. We'll factor out that dy over dx. That's kind of the slick little trick I talked about on the previous slide here. And now we're going to go ahead and divide both sides by what's in the parentheses here to get dy over dx equal to 2 over 2y minus 3. And voila, there it is. Okay, let's go on to this next example on the right here. And it might seem like it's a little tricky, but it's not too bad. The derivative of 2x is just 2. The derivative of e to the y is e to the y, but since I'm differentiating a function that's got a y in it, I have to tack on dy over dx. And then that's going to be 2x minus 2y dy over dx over there. Okay, so now what I need to do is I need to move some things around once again, and I need to see if I can get the dy over dx by itself. So we'll send the 2 over to the other side, pull the 2y dy dx back over here. Take care of that all in one fell swoop if we can. So e to the y dy over dx plus 2y dy over dx, and then 2x minus 2. And now time to factor. And now I'm going to go ahead and divide both sides by the parentheses. So you get 2x minus 2 over e to the y plus 2y, and that's about where it ends up. Okay, let's go on down to the next one here. Ooh, we've got a product rule situation brewing here, and that has to do with the 2xy. So I want you to think of the 2x as your u, and think of the y as your v. Okay, so let's apply the product rule first on the left side. U prime is just going to be 2, and v is going to be y. And then we have our u, and then our v prime. Well, the derivative of y is just going to be 1, but you have to tack on that pesky dy over dx. Okay, now on the right side, I'm going to get 6y dy over dx plus 2. All right, so once again, I'm going to need to do some shuffling here, and that's not going to take too much work. Just, a step or two of algebra, just be careful with it. So you get 2x dy over dx minus 6y dy over dx, and then 2 minus 2y over here. All right, so dy over dx when we factor times the quantity of 2x minus 6y, and then 2 minus 2y, and now we divide, and that is our derivative, but not quite, because today is a day that ends in y. So we're going to go ahead and factor out a 2. And now we're going to say goodbye to that 2. Goodbye, 2. And we have 1 minus y over x minus 3y. And that is our dy over dx. Okay, not so bad. Jump over here. Ooh, another product rule situation brewing. This one's going to need a little bit of extra care. So let's see what we can do with this. All right, left side, 15x squared. And then the plus 3 drops out when you take the derivative. A lot of students, if you're going to make a mistake, it's going to be right here where you forget to take out that constant when you derive. Okay, so it goes to 0. On the right side, I have 2 dy over dx minus, okay, now when I do a product rule and there's a minus involved in front of it, I'm going to have to open up some parentheses to make sure this is done correctly. So again, here's your u, and here's your v. So u prime, 6x, and your v is y. And then u, and then v prime. Well, that's just going to be dy over dx. Okay, a little bit of a mess, but we're almost there. So 15x squared, 2 dy over dx. And now, careful, we need to distribute this negative. So we get negative 6xy minus 3x squared dy over dx. All right, well, probably the fastest thing to do here is going to be to pull this negative 6xy over. And I'm going to go ahead and factor out our dy over dx from the remaining terms. So dy over dx is going to be the 15x squared plus 6xy all over 2 minus 3x squared. About as far as I can go on that one. And here's our last question here. In terms of y, describe the values for which that curve, x cubed plus y cubed, equals 4xy plus 1 will have a vertical tangent. Ooh, a vertical tangent. Okay, well, what does that mean? Well, let's go on and talk about this next one because it asks about the same curve and where it will have a horizontal tangent. All right, well, that must mean that dy over dx is going to be 0 for a horizontal tangent, and for a vertical tangent, dy over dx must go undefined. Okay, now why is that the case? Because horizontal lines have a 0 slope, vertical lines have a slope that is undefined. Okay, so now we need to go and analyze the derivative here and see what we come up with. So let's go to work on that. So okay, so picking up on that, 3x squared plus 3y squared dy over dx. Okay, now we got a product rule situation on the right side. So it's going to be 4 times y plus 4x dy over dx. And then, just as a heads up, this plus 1 is going to drop out. Okay, so now we've got a little algebra to do. I'm going to push the 3x squared over to the other side, pull the 4x back over this way. We get 3y squared dy dx minus 4x dy dx is equal to 4y minus 3x squared. Okay, so let's take the step of factoring out. And then let's go ahead and divide to get the dy over dx accounted for. Okay, so there is our derivative. Okay, so now I still need to figure out where we're going to have a vertical tangent, and that's going to be where dy over dx is undefined. Well, what's going to make that go undefined? When this 3y squared minus 4x, when that goes to 0, that's going to be where we have a vertical tangent. That's going to be when 3y squared minus 4x is equal to 0. Okay, well, solving this is going to be kind of a challenge. I'm going to solve this for x, actually. I'm going to solve this as an interesting little relationship here, where x is equal to 3/4 y squared. Okay, so what does this mean? This means at any point on the curve, x and 3/4 y squared, that's where that's going to go undefined. Okay, kind of a strange explanation. We'll probably look at this in class and look at the different situations that are going on here. Okay, now for the horizontal tangent, it's a little bit more interesting here. So we've got where the numerator, the 4y minus 3x squared, where that's going to go to 0. Okay. So now that's all well and good, but we could probably figure out exactly where that is on the curve itself. And how can we do that? Well, strangely enough, we can pull off a substitution. But I'm going to discuss a little bit more of this in class to lead off our next session. So we'll pause right here for now, and we'll pick this up in class.